Thank you. Thank you for the invitation. I realize I'm somewhat of an imposter in our model theory meeting. So my talk will be about a forcing construction, but towards the end of it, I will say some stuff about iteration of extenders that may be of interest to this crowd. Also, it's nice to see all the mouse t-shirts. Okay, so the theorem I will be talking about is joint work with my postdoc, Tom Benhamel. Which says the following. So from large cardinals, one can force a model where you have the failure of the SCH at alpha omega 1 plus alpha omega 1 together with stationary reflection at alpha omega 1 plus 1. So this will be the result that I'm going to be talking about. But first, let me start with a little bit of motivation and some like historical and some background results and why we were interested in this. So in general, when one looks at these two principles, the failure of SCH and the principle of stationary reflection, there is this sort of tension between them. So why? Stationary reflection is a compactness type principle. You know, it's meaning if something holds at below kappa, it will hold at kappa. While the failure of SCH is an instance of incompactness because it says that you have this singular cardinal such that the power set function is small below kappa but blows up at kappa. And this is the reason for both the challenge and the interest in combining these two principles together. Also, on the other hand, as we know, you need large cardinals to get the consistency of either one of them. So what do we know just about the consistency of them separately? So this is goes back to two classical results of Menahem. Late 70s. So from a supercompact, so S dot C dot for me always means supercompact, can force failure of SCH at alpha omega, and of course later by works of Gittik, Woodin, and Mitchell, the large cardinal hypothesis was optimally reduced. And early 80s, from omega many supercompacts can force reflection at alpha omega plus 1. Okay. And just two quick notes. The forcing for the first result was a supercompact Prickry forcing, and the forcing in the second result was an iteration of Levy collapses. So one takes the most natural thing. Infinitely many supercompact cardinals kappa n's, and with Levy collapses, you turn them into the alphans. And one notes that, so in this construction, SCH holds. Actually, GCH holds. And in the above construction, via an argument I'll mention in a minute, reflection at the successor of the singular fails. So then the question is, can we combine both of them? What about both together? And in recent years, maybe in the last 5 or so years, there were various papers showing that, yes, one can combine both of them. So let me just, well, I'm just going to mention, so the way the history went, it's easier to combine reflection with failure of SCH at some cardinal kappa high up. It's significantly harder when one wants to put in collapses. So the way the results went is first it was shown that one can consistently have reflection at kappa plus with failure of SCH at kappa. Then later it was brought down to aleph omega. So the answer is yes. And this is due to a paper of myself and 2 co-authors, and also independently by Ben-Neria, Hayut, and Unger. So yes, let me say. I'm just doing alphabetical. And with a different construction, it was also shown by Homer, Spencer, and Yair. Okay. And so then the next question is, because this was, yes, for aleph omega, so countable cofinality. So the next question, well, what about uncountable cofinality, or let's say our favorite singular cardinal of uncountable cofinality, aleph omega 1. And this leads me to the theorem I'm going to talk about that we showed with Tom that yes, one can indeed do this. Any questions so far? Okay. Mm-hmm. Okay, yeah, I would expect these questions from this conference. Yeah, so for the failure of SCH, it's a Mitchell cardinal kappa, measurable kappa of Mitchell order kappa double plus. Now, for reflection, of course, it's not known because there's no yet inner model for a supercompact, but for a reflection at the successor of a singular, it's as high as it goes. So the conjecture is that it will be supercompact. Now, let me make one note here. So the original reflection at aleph omega plus 1 was done from omega many supercompacts. Then in a different paper, around this time, but a little bit before, by Spencer and Yair, they reduced this consistency strength to 1 supercompact cardinal. But so for reflection, supercompactors. All right, and okay, so I want to give a couple of points that lead to the idea of the proof. Of course, I'm not gonna actually do the proof, but I want to somehow describe what goes into this forcing, and I think it's for the sake of appealing and understanding it, I'm going to start with something quite simple. So, just what is the general idea when you want to combine, when you want to do failure of SCH? I mean, you want to do some sort of prickly forcing. What is the general idea when you want to do reflection? Well, I mean, you start with some large cardinals, possibly you do some forcing, and then you want to somehow use lifted embeddings to get that reflection. So, just to get, this is in general methods, not necessarily in this specific theorem, but to get failure of SCH, one use some sort of a prickly type forcing, and to get reflection, what do you use? I mean, you have to lift some elementary embedding, right? You use some large cardinals in a prior universe, lift the embedding, and some sort of stationary set preservation to get your reflection. So when one tries to attack this problem, I mean, the first question people asked, back when they were wondering about combining these two, is okay, well, let's do like the most simple thing, vanilla prickly, and see what happens with reflection in that model. So first question, if you take V and then just vanilla pre-cre at kappa. Question. What can you say about this model and reflection at kappa plus? I mean, does it hold? Does it not hold? When I say vanilla pre-cre, I just mean start with a measurable cardinal kappa and singularize it using a normal measure. And like maybe the first result about this that I know, and it turns out it's quite motivational for even the more complicated constructions later, was due to Cummings, Foreman, and Magidor from that paper, Scale, Squares, and Stationary Reflection from like around 2000, who showed that, so let P, or at least that's, yeah, it was in that paper appeared first, let P be vanilla pre-cre at kappa. So one can do several things. So first in VP, which means just any generic extension of P. So there is one set that doesn't reflect, for sure. Now kappa plus intersection Coff V kappa doesn't reflect. I mean, it cannot possibly, right? Because this set didn't reflect back in V, and there is no reason why all of a sudden it will magically reflect in a generic extension. But not always bad. On the other hand, if in V kappa is kappa plus supercompact, then this is the only obstacle for reflection. For all the other sets, you do get reflection. Then you do get reflection for everything else. So kappa plus restricted to points of V cofinality less than kappa. And I'll actually sketch the proof of this because it's really very motivational into the proof of these later theorems about SCH and failure of SCH and reflection. So proof sketch. And this will probably be the only proof of sorts I'll do, so don't worry. Okay, well, what does one do? I mean, to get reflection, what? You need to lift some elementary embeddings. Here, you don't really need to lift it, but you do need to go back to V where kappa is supercompact. So let S dot be a name for a stationary set in kappa plus Coff V less kappa. Okay. So we want to show that this reflects. So working in V, for every, so we're just working in V, for every stem, so when I say stem, I mean a pre-cre stem. So the pre-cre conditions are a finite increasing sequence of ordinals in kappa followed by a measure one set. So for any such finite increasing sequence, of ordinals in kappa for every stem H, one can look at what I like to call the traces of the stationary set with respect to H. So these guys are the set of all ordinals alpha such that some condition with a stem H forces that alpha is in S. Exists P with stem H, so P is of the form H follow the measure one set. Let me write it, i.e. P equals H followed by some measure one set such that P forces alpha is in S dot. Okay. And now we're working in V, where we have reflection how that kappa plus as long as you restrict to Coff V less than kappa. And the first observation is that for some H, and actually for many of them, SH is stationary. Now here in V, and that's because there are kappa many stems, and we're talking about sets in kappa plus. And therefore, since also we have reflection modes in V, as long as you restrict, oh, I see what Ralph meant. Okay. As long as you restrict to points of cofinality less than kappa, we have SH reflects. And since SH reflects, it takes a little bit of an argument using the fact that the direct extension order is kappa closed to get, oh, therefore, no, S dot is forced to reflect. So one gets a witness that SH reflects. Now this is a, will be a stationary set of order type less than kappa, and using the fact that you can intersect less than kappa measure one sets, you can find a condition that decides exactly, that initial segment showing that SH reflects. So this is, okay, a very nice, kind of straightforward proof, but it turns out that this simple proof actually contains many of the ideas that we ended up using. Okay. All right. Okay, so if I wanna summarize this, is you take a name for a stationary set, you somehow in V, in the place where you do have elementary embeddings, you look at traces, and you argue, well, since some of those traces must be themselves stationary, then they reflect, and then we get reflection in the final model. Okay, so now, okay, what do we do in this theorem? Well, let me call it our precre, although not really our, it was a concept that Moti defined, Moti's precre, is, so let me just say what is the large cardinal hypothesis. So we start with omega-1 many supercompact cardinals. Well, why omega-1 many? I mean, we're going to do this for cofinality omega-1, let's say with limit kappa. And what we want is we want to force, with a precre type forcing, to kill SCH at kappa. Now, here kappa is already singular. The way one forces to violate SCH by singularizing kappa, usually the method is you add many subsets of kappa with a Cohen forcing, and then you singularize kappa. What we're going to do, what one does in this situation is start with a kappa that's already singular, and the precre forcing itself will force failure of SCH by adding many, so let me call it P again. So P will add, well, how many? I guess kappa double plus many precre sequences through through the product, through the kappa i's, thereby making, while preserving the strong limitness of kappa, making kappa have power set kappa double plus. And so what do we use to add these many precre sequences? Well, we use something called overlapping extenders. So using extenders, so in a diagonal way, overlapping, something called overlapping extenders on each of the kappa i's. On the kappa i's. Okay, so I haven't talked about, I'm not going to talk about mice and such, but I am talking about extenders. So that's one respectable word here. And I'm going to also iterate those extenders, so even better. I'm going to be talking about two types of iterations. One is the forcing iteration, but towards the end of the talk, I'll say something that will resemble more of the extender iterations from the talks like John's talk. Okay. All right. All right. Oh, by the way, I did this, example about the vanilla prickly forcing. Let me say a little bit about what happens if instead of vanilla prickly one puts vanilla Magidor. So just usual Magidor forcing, since we're talking about cofinalities, uncountable cofinalities. Well, the same ends up being true. So, or the analogous results are true if you, instead of P, you consider the Magidor forcing to singularize kappa of uncountable cofinality. So it's code for the Magidor forcing to singularize to uncountable cofinality. Okay. Okay, so now what this forcing P does, so when we force with Motis overlapping extenders, so we have SCH failing at kappa. Also, one can interleave collapses to make kappa equal to alpha omega 1. And the construction of, so now P here is Motis forcing overlapping extenders. Extenders with interleaved collapses. And this was due to a student of James sitting on, but don't know how to. I never know how to spell his last name. But how do you spell it? Is it easier to spell? I-N? No. Okay. Okay. So yeah, so he did this in his thesis, and maybe there is also a published paper. I don't know, but it's very nicely written. So if anybody who wants to learn about overlapping extenders with interleaf collapses, I recommend reading his thesis. Okay, so now what do we want to do next? Well, we want to get reflection. So let's take this model and look at what happens with reflection properties. And it turns out that something similar to this picture happens. So now that we no longer have this offending non-reflecting set because there's no cov V kappa points anymore, because kappa was singular, but we still do have some non-reflecting stationary sets. And question, which sets reflect in VP? Let's talk about this question here. So let's take let's take it here. Let's take a stationary subset of kappa plus. And so what is the idea? Now, this has points of cofinality less than kappa, so by shrinking it if need be, I mean, we may as well assume that the cofinality is bounded by some, let's say, less than kappa I bar. Okay? So now going back to V, I mean, we took the kappa i's to be supercompact. So, the natural way is, well, maybe I go to a universe when kappa I is supercompact and use this to show that some sort of trace of S reflects. Okay. Let me actually just do I. So what we want, the idea is go to an inner model. Oh, yeah, I did say inner model. So something possibly not quite the ground model, but let me just say. I'm sorry, I just have to say a model. Go to a model W where we have reflection at kappa plus intersection of less than kappa I. Now that any model where kappa I is supercompact will satisfy this property. So if kappa is supercompact, then you can get sets of kappa plus, cardinals above kappa I with points of small cofinality to reflect. And so this is one thing we want from W. And W knows something about traces of S dot. Or about something about traces. And I'll define traces in a minute, S dot, okay? So the W in question in this simple case was just V, okay? Now, here our forcing is much more complicated, so W will be, will contain V. It will not be quite an inner model of the final extension, but somehow orthogonal to it. Also, in this motivational case, the traces were determined by picking a stem and looking at all points such that a condition with a certain stem decides them. Here, we're not going to quite pick a stem because there are too many stems when you force with extenders. You blow up, so you cannot use this pigeonhole principle that one of them is stationary. Instead, we're going to pick a psi. So what are the traces? What are the traces? These traces. And again, if it's starting to feel technical, just look at this board. So by traces, I mean the analogs of the SHs in this more complicated forcing. What are the traces? Well, for a fixed I psi less than ω1, it turns out that this forcing, like most Frick forcings for uncountable cofinalities, going back to the Magidor forcing, also the radiant forcing, etc., can be split into a lower part, the Frick sequences that you're forcing up to kappas of psi, and an upper part. So one can, I'm oversimplifying it a little bit, but one can split P to a lower part and an upper part, okay? Where you can think of this guy as doing what P does, but when you replace ω1 by psi, so here, psi's limit. And this guy has good closure. So this is somewhat small. It's not too small. There is still some poses to deal with, but this guy has good closure. Closure with respect to, the so-called direct extension order, where you do not increase the stem of the pre-conditions. Okay, and with appropriate labor preparation, the fact that this has good closure using indestructibility, we can arrange that in V greater than Xi, you have reflection. So this will be our model W. P greater than Xi, but with this restricted to the direct extension order, because we want it to be closed. Now, this model is not exactly a submodel of the final extension. It's kind of orthogonal to it. And it's really the higher analog of our W here was V, right? Because here, when you take the direct extension, you just get the trivial forcing. Here, you get more stuff, but you can arrange reflection. So now, in order to look at the traces, one can define S dots of, now, I'll raise the board in a minute. So this is a trace, S dots of Xi. So this will be the set of all pairs. So it's going to be a name, alpha comma P, such that P is in so let me Oh, no, okay, no, sorry. I mean, actually. Oh, but let me, I actually need to talk a little bit about the small forcing before defining the traces. So, since we have closure in this guy, we can, it's actually direct closure with labor indestructibility. You can arrange kappa Xi to be Q super compact here, okay? And now I said that this later forcing is small. It's not too small. It's not of size less than kappa Xi, but most of its parts are. So one can lift an embedding to the bigger model V Xi, where this is both parts, but with the direct extension order. So, okay. Oh, and before I do, so you get reflection in this model too. Okay, and now for my traces, S dots of Xi will be alpha P, such that P forces, so far very similar to, to how one defined the traces in the simpler case, alpha in dot S, and now we want I haven't defined the notation, but let me say max of stem of P, whatever that is in this more complicated case, is less than or equal to Xi. Now note it's a P name. I mean, it's a name because ordinals and conditions, but one can also take this order, and this is both a P name and a psi name, depending on which order I take. And now, and this is my trace, the interpretation of this guy with respect to a generic for psi. And we can show that if the trace, so this is kind of a key lemma, if the trace, which is this S dots of psi interpreted by generic from psi, if the trace is stationary, then it reflects. And of course, here the argument that it reflects is more involved because you have to lift embeddings, etc. But morally, I mean, it goes back to this basic idea. You use the fact that you have those lifted embeddings in W, and since this is a stationary set, it will reflect. This requires a separate lemma. Okay. It reflects where? I should say where. Okay. So it reflects in the pixie. But then there is another lemma. I don't know. Which, I mean, requires quite an argument. So that's why I want to give it a separate lemma name. And from there, one can show with some work that it reflects in VP. All right, so now this gives us an analysis of the sets that do not reflect, just by using, taking the contrapositive. So if you have a stationary set that doesn't reflect, it must have been such that all of its traces are non-stationary. And let me write it here. So moral of the story, non-reflecting sets in VP have non-stationary traces. Okay. And also it turns out, and we gave these sets a name, so we call them, let's call them fragile. Why fragile? Well, because we want to kill them, and it's easier to kill something fragile. So it's a motivational pattern. So let's call them fragile. And it turns out that this whole analysis leading up to this final talking point holds not only for P being the original, I mean, the overlapping extender-based forcing with collapses, but also for any forcing that has the nice Prikry-type properties of P. Can be, I'm just going to say it. Also true for many Prikry-type forcings with the properties of P. Okay, so then what do we do next? I guess next we should have a break soon, but we have to kill all those fragile sets via some sort of an iteration of length kappa double plus. So let me, oh no, I have until 10 or until, okay. Okay, so 4 minutes to iterate. Maybe. Okay. So then, what the main construction is, it's an iteration of length, write it like this, kappa double plus, such that the very first step P0 is the overlapping extender forcing with interleaf collapses. So at the very first step, we get kappa to be alpha omega 1 and SCH failing at kappa. And then at successor, so at limits, we take kappa support. At limits. And at successors, P alpha plus 1. So we want to kill the, using some bookkeeping function, the alphas, if relevant, fragile set. Well, if, so. I guess it would have been more accurate to write it. The bookkeeping function gives us a set. If that set is non-reflecting, therefore it must have been fragile, and we're gonna shoot a club through it. Otherwise, we just do the trivial forcing. And it turns out that this works. Now, one important point about this successor step is that given so you can think of this as the forcing the full iteration at stage alpha plus 1. This is why I wrote it like this. So in particular, this projects to P alpha. It turns out that as long as you're trying to kill a fragile stationary set first, you can without destroying other cardinals, but also you can do it in a prickly way. So assuming if P alpha is prickly, type forcing with the right properties to conduct this analysis, you can construct the next step forcing P alpha plus 1, which is also a prickly type forcing. And this is why we can go on with this iteration, okay? Forcing iteration. Until they're not. And also, I mean, it's non-trivial to prove that these prickly properties of the forcing posets are preserved at limit stages. So that takes some time. And I don't have time to talk about how one kills this alpha fragile set, except to say that you use the fact that it's fragile. So, well, maybe I'll say something. So how do we shoot a club through the complement of a stationary set? Well, with closed bounded sets, right? What could possibly go wrong if you try to prove, that, like, why is this forcing not closed? Well, it's because if you have an increasing sequence increasing in strength sequence of conditions, I mean, you can take their union, but then the supremum of the points may all of a sudden be in your stationary set, right? This is what may go wrong. Well, here we use the fact that the traces are non-stationary to pick names for clubs in the complements of those traces, and we require, when we force this club through the complement of our set, that it uses closed bounded sets whose maximum is actually in those clubs disjoint from the traces. And this somehow lets us catch our tail so that the sub of points not in S remains not in S, in a nutshell. Okay, now I have like 1 minute, and I promised that I'll say something about the iteration as you guys know it. So it turns out that many of these forcings, I mean, starting from vanilla prickly, but also this extender-based forcing, can be analyzed as follows. So you can actually take these extenders for which this forcing is defined and iterate them. So take, consider the maps from the extender and then the maps from those ultra powers, etc. It's, I guess, the simplest situation that one can consider is if you take just one normal measure and you have a prickly forcing for it. So you take J of U, then J of U, and you iterate omega many times. Okay? And so this is kind of an old fact that if you take the sequence of the critical points, this gives you a generic filter for the usual vanilla prickly on the J side. And there's been some very interesting analysis in recent years, not so much by myself, but I'm reading on it because I'm interested in it, but mostly by the people that were written here, but mostly by Yair and also Spencer and Omer, about what happens when you iterate, somewhat more complicated, in more complicated cases than just the one measure. So they show that one can iterate extenders in a way that you guys know how to, I think. And by using at various critical points, you get a generic object on the J side. So what is known about this, as a reference, I'll give a paper very recently somewhat recently, on the archive by Yair. But there is also many cases for which those obtaining generics by iterating the embeddings remains open, like in this case, it's open. Or in cases where you have somehow these diagonal extenders and you want to put collapses. So that's open. So there is probably at least some relation between this forcing and iteration of extenders, as you guys know how to do. So yeah, I wanted to end with that.